We've spent a good bit of time together now talking about adding, subtracting, and multiplying fractions. I'd like to spend a little more time talking about fractions in this lesson by talking about division by fractions. The first comment I'd like to make about division with fractions is this. In a very real way, division with fractions is the opposite of multiplication with fractions. That means that we would expect the steps to complete a division will look somewhat similar to the steps for multiplication. And it turns out that that's exactly the case. The second comment to make is this. As with some of the other material we've already covered in this course, it'll be very important to follow the steps that I outline in the examples that we're about to complete. The steps of the process and the order of those steps is very, very important. So let's get started with a quick example. I'd like to find 2/3 divided by 4/11. Now, as we begin this first example, let me tell you the steps that need to be completed to finish the problem. First, we're going to write down the fraction 2/3 as it is. We don't do anything to that first fraction anytime we're doing a fraction divided by another fraction. Secondly, we're going to switch the division symbol to a multiplication symbol. That's right, every time you encounter a division problem with two fractions, it turns out that we will rewrite it almost immediately into a multiplication problem instead of a division problem. And then thirdly, we need to write down the reciprocal of the second fraction. That's the 4/11. Now, what is the reciprocal of a fraction? Well, it's simply the fraction that has the numerator and denominator switched. So the reciprocal of 4/11 is 11/4. It's that simple. So the original problem, 2/3 divided by 4/11, will have the exact same answer as the multiplication problem, 2/3 times 11/4. Do you see what we've done? We switched the division to a multiplication, and we switched the second fraction to its reciprocal. And notice that we did not touch the first fraction in the problem. It remains the same every time. But now, I hope that you realize that we're staring at a problem that we learned to do in a previous lesson. And that's excellent. By the way, this happens sometimes in mathematics. In fact, it happens a lot. We often refer to it as reducing a problem to a previous type of problem, which is often easier to handle or is at least a type of problem that we've learned to handle in the past. So now we've taken this division problem with two fractions and turned it into a multiplication problem with two fractions, and now we know how to handle that. We're working with 2/3 times 11/4. So let's do the multiplication. Do you see any cancellations that we could be doing the same way we did in the previous lesson? Sure, the 2 and the 4 both can be divided by 2. And that would then give us 1/3 times 11/2. And after I've done that cancellation, I have to be honest, I don't see any others there. So now we go ahead and just multiply the numerators and multiply the denominators, and that's going to give us the fraction 11/6. That's our final answer. Now, it's an improper fraction, right? Because the 11 is larger than the 6. And if you don't want to leave your answer as an improper fraction, you can rewrite it as a mixed number. And in this case, 11/6 is the same as 1 5/6. Now, let's work on a second example just to make sure we have the steps down before we start to make things too complicated. I would like to suggest that you try this one yourself first. Calculate 5/9 divided by 20/27. Okay, first things first. We've got to replace that division symbol by a multiplication symbol, and then we have to replace the 20/27 with its reciprocal. And once I've done that, the original problem turns into 5/9 times 27/20. Again, notice that the 5/9 did not get changed in any way. That first fraction always just stays the same. It's the second fraction that gets turned into its reciprocal when we switch from division to multiplication. Now, before we start the multiplying, let's do as much canceling as we can. Notice that the 5 and the 20 both have a 5 in them, so we can cancel out that common divisor of 5 from both of those pieces, and that's going to leave us the multiplication problem 1 over 9 times 27 over 4. Next, I look at that 9 and that 27, and they both definitely have a 3 in them. Actually, they both have a 9 in them, don't they? So I would say we could cancel out a 9 from both the numerator and the denominator. We might as well go with that. And that will then give us 1 over 1 times 3 over 4. Because 9 divided by 9 is 1, and 27 divided by 9 is 3. Well, now we can easily handle the multiplication of the numerators and the denominators as long as we're careful about it. 1 times 3 is 3, and 1 times 4 is 4. So our answer is simply 3 over 4, or 3/4. And that's really nice. The original problem, which looked a bit messy at first when we're dividing one fraction by another, simplifies to the answer 3 over 4. Now, I'd like to move to another division problem with two fractions, which at first might catch you a bit off guard. So let me just mention the problem, and then we'll talk about what's happening with it. I'd like to calculate 3/7 divided by 3/7. Now, before we jump into the example too quickly, I want us to stop and think for just a second. Actually, pausing or stopping and thinking are some important skills in a mathematics course. So it's wise to really pause for just a moment here and think about what's happening. Let's think by answering the following questions. What if I asked you to divide 5 by 5? What is 5 divided by 5? Well, it's just 1. What is 7 divided by 7? The answer there is also 1. What is 23 divided by 23? Well, that answer is also 1. It seems like there's a pattern here in the examples I just gave you. When you divide something by itself, the answer you're supposed to get is 1. Even if we did 1,000 divided by 1,000, we would still get 1. So, does that pattern carry over to fractions? When you divide one fraction by itself, by the same fraction, do we get 1 as the answer? Well, let's check by walking through the steps of this example to see if 3/7 divided by 3/7 also gives us 1. Okay, let's do the steps the way we're supposed to do them. We're supposed to change the division symbol to a multiplication symbol and then replace the second fraction with its reciprocal. In this case, that would be 7/3. So the original problem can be rewritten as 3/7 times 7 over 3. Now notice that the 3's will cancel, and that will leave you with 1 over 7 times 7 over 1. And the same sort of cancellation will happen with the 7's. They can both be canceled, and that will leave us with 1 over 1 times 1 over 1. Well, I can't make it any simpler than that. 1 times 1 is 1, and so the numerator and the denominator are both equal to 1. And that gives me a final answer of 1 over 1, which is just the same as 1. So what does that mean? It means the following. When we divide a fraction by itself, you're going to get 1 as the answer, just like with whole numbers. And that's going to be true of division for every fraction except for 1. If the fraction that you're dealing with represents the number 0, remember, you can never divide by 0. So that pattern is not going to work if the numbers are 0 divided by 0. But otherwise, no matter what fraction you divide by itself, as long as it's not 0, the answer is going to equal 1. And that means, as an example, if I take 575 divided by 9, or the fraction 575 over 9, and then divide that by 575 over 9, the same fraction again, the answer is going to be 1 automatically, because I'm just dividing the same fraction by itself. This is a great trick to remember, or a great rule to remember. Anytime you divide a non-zero fraction by itself, you will always get the answer of 1. Now, I'd like to switch gears just a bit and move to another division problem with two fractions, just to make sure that we can see some of the different things that occur when we're working through these kinds of division problems. So here's an example I'd like to look at. Calculate 12 over 5 divided by 5 over 2. Now, I wanted to show this example to you with a very specific goal in mind. There's a very common pitfall that some students will fall into, and I'd like you to avoid it here. My hope is that when some of you first saw this problem, you immediately wanted to start canceling those 5s and maybe even cancel a 2 from the 12 and the 2. And I can completely understand that temptation, but it's wrong. And it's wrong because of the following. You should never perform cancellations in a division problem like this when the division symbol is still present in the problem. You can only start canceling the numerators and denominators in different fractions after you have switched the problem from a division problem to a multiplication problem. So what does that mean in this example? Well, before you can do anything else, you've got to remember to switch the division to a multiplication symbol and then replace the second fraction with its reciprocal. That reciprocal has to be written down before you can do any cancellation. So the original problem, which was 12 over 5 divided by 5 over 2, can be rewritten as 12 over 5, leave it alone, times 2 over 5. Now that we've done the switch to a multiplication and we've written the reciprocal, now you can do cancellations if they're available. And only now. You can't do them before. But of course now if you look, there aren't any common factors between the numerators and the denominators any longer. And so that temptation to cancel at the beginning of the problem, which is a very dangerous temptation here, is now gone because I can't cancel any of those numerators and denominators any longer now that I've written it as a multiplication. So what do? Well, I simply multiply. If I can't do any cancellation, I just multiply the numerators and I multiply the denominators. So 12 times 2 equals 24, and 5 times 5 equals 25. And that means that my final answer in this division problem is 24 over 25, and believe it or not, that's already in reduced form. And it's not an improper fraction because 24 is smaller than 25. So that means 24 over 25 is going to be less than 1, and that means that the final answer really is 24 over 25. So before I go anywhere else, let me just again remind you, don't do any cancellations of a numerator in one fraction and a denominator in another fraction in a division problem until you have rewritten it as a multiplication problem and switched that second fraction into its reciprocal. Now, let's switch gears and look at a few other kinds of problems that can arise when we're handling division involving fractions. Some of the problems might even look a bit strange. Don't worry about them. Just take a deep breath and follow the steps that we've already discussed. It's always important in mathematics, especially in these fundamentals of mathematics. You've got to make sure you know the steps and that you follow those steps one at a time very, very carefully as you walk through these problems. So let's look at the following. Let's calculate 12 over 17 divided by 8. Now, I can almost hear some of you saying, oh my word, how am I going to do this? There's an 8 there. It's not a fraction. How am I supposed to handle that? Well, you can handle this. It may not look like a fraction, but it certainly is equivalent to a fraction. Remember, every whole number that you see can be rewritten as a fraction with a denominator of 1. So, what am I going to do in this problem? I'm going to replace the whole number 8 with the fraction 8 over 1. And that means that what we started with as the original problem is going to be rewritten as 12 over 17 divided by 8 over 1. Now that shouldn't look so bad. We've done a few problems already in this lesson that had that kind of a look. So let me suggest that you consider finishing this problem on your own, and then we'll come back in just a moment and make sure that you've got the right answer. Now, what do? Well, we're going to replace that division symbol by a multiplication symbol, and then I'm going to change that 8 over 1 to its reciprocal, which is 1 over 8. So now I've gone through 2 steps of the process, and the original problem has the same answer as the multiplication problem, 12 over 17 times 1 over 8. And now we just do things the way we've done them before when we are multiplying 2 fractions. First, I see, now that I have a multiplication symbol, that I can do some canceling between the 12 in the numerator and the 8 in the other fraction's denominator. Both 12 and 8 are even, so they both have a 2 that can be divided out of them and canceled out. Actually, they really both have a 4 in them, which can be divided out. And so I'm going to suggest that we just jump right to dividing them both by 4 and canceling out that 4. So when I do that, I'm going to have 12 over 4, which is 3, and 8 over 4, which is 2. And so I'm going to replace the numerator of 12 with a 3, and I'm going to replace that denominator of 8 with a 2. And our problem then is going to be rewritten as 3 over 17 times 1/2, or 1 over 2. Well, now where do we go from there? Well, I don't see any more cancellation that can be done between a 3 over 17 and a 1/2, and so there's really no more simplification we can do. We just multiply. But thankfully, instead of having to multiply big numbers together, we've whittled things down with cancellation in order to have the multiplication go quickly. In this case, we multiply our numerators, and we have 3 times 1, which is equal to 3, and the denominators give me 17 times 2, which is equal to 34. So my answer looks like 3 over 34. Now we should stop and ask ourselves, is that in lowest terms? You're probably tired of me asking that question at the end of every one of these problems, but we really do need to know, is our fraction in lowest terms? Well, the 3 in the numerator only has 3 and 1 as factors. Then I need to ask, does the 3 divide the 34? Which it does not. You can try that with long division if you'd like, but you'll end up with a remainder that's bigger than 0 in that case. And so 3 over 34 cannot be reduced any farther. 3 over 34 is in lowest terms, and that's my final answer. Now, I'd like to try another example which is sort of a cousin of the one that we just did, but hopefully you'll see that it's similar and yet different at the same time. Here's the example I'd like us to look at. Let's calculate 6 divided by 4/9. In fact, if you're feeling brave right now, why don't you try it yourself, and then we'll come back together and see how you did. Okay? As before, don't fall into the trap of doing any cancellations too early in the process. Cancellations have to wait for a couple other steps to be done first. So let's walk through this step by step and make sure that we do everything safely, so to speak, or correctly. Maybe that's a better way to say it. First, what do we do with that 6? It's a whole number. I need to change it somehow. Otherwise, I don't really know how to handle the problem. But I've seen this trick before. 6 can be rewritten as a fraction with a 1 as a denominator. So 6 is the same as 6 over 1. And that means that my original problem can be rewritten as 6 over 1 divided by 4 over 9, or 4/9. Okay? That looks like a standard fraction division problem like we've talked about before. Now you might at that point try to do canceling. Don't do it. You can't do it yet. You haven't switched the problem to a multiplication problem just yet. So let's do that now. Switch the division symbol to a multiplication symbol, and at the same time, flip that second fraction into its reciprocal. Don't forget, second fraction has to be flipped over into its reciprocal. The first fraction doesn't get touched at all. So now the problem changes from a division problem to a multiplication problem, and that multiplication problem is 6 over 1 times 9 over 4. And now, and only now, can you start that canceling. Okay, and now if you look at those numerators and denominators to see if there are any common factors, you should see that the 6 in the numerator and the 4 in the other fraction's denominator are both even. That means they both have a 2 in them, and those 2's can be canceled out. And that then is going to give us 3 over 1 times 9 over 2. Remember, 6 divided by 2 is 3. That's why the numerator of the first fraction becomes a 3. And 4 over 2 is 2. That's why the denominator of the second fraction becomes 2. So I have 3 over 1 times 9 over 2. And there is no more cancellation that can be done. Now you might be thinking, and I haven't really talked about this up to this point, that the 3 and the 9 could have cancellation done. They can't because they're both in the numerator. Don't touch those. They can't be canceled in any way. You can only cancel a numerator or a piece of a numerator with a denominator or a piece of a denominator. Okay? So 3 over 1 times 9 over 2, you just have to go through the multiplication now, and that's going to give you 27 on top, 3 times 9 is 27, and 2 on the bottom, 2 times 1 is 2. And so your answer is 27 over 2. Now that's an improper fraction. And since the 2 goes into 27 a total of 13 times, with a remainder of 1, our final answer can be rewritten as a mixed number, and that would be the mixed number 13 and 1/2. Now, before we move on to some more examples, let me also mention some different kinds of notations that can arise when you're dealing with a division problem involving fractions. First of all, you may have seen in some textbooks or in some of your other work in the past, something like the fraction 2/3 and then another fraction bar being, in other words, being divided by 4 over 15. This is known as a compound fraction when you have 2/3 over 4 over 15. It basically is simply saying, as a compound fraction, hey, let's find 2/3 divided by 4 over 15. So you can rewrite any compound fraction you see that way as a division problem. And in this case, it would just be 2/3 divided by 4/15, or 4 over 15. Once you've rewritten the problem in that fashion, you know exactly how to handle the problem because we've done several examples of that kind already in this lesson. So anytime you see a compound fraction like that, just rewrite it as a division problem. One fraction divided by the second fraction, and you'll be good to go to finish out the problem. Now, let's work on some other types of division problems that involve fractions. This time, not so much with compound fractions, but with mixed numbers, okay? So here's the example I want us to look at. Let's calculate 7 3/5 divided by 3 4/10. Now, there aren't any worries here. It may look a little complicated, but just work through the steps with me and we'll be fine. What do you think the first thing to do is in this example? Well, if you said switching those mixed numbers into improper fractions, you would be exactly right. The first thing you want to do is convert those mixed numbers into improper fractions. I don't know if you remember, but when we were doing multiplication of fractions, that was also the first thing you wanted to do when you saw mixed numbers. Convert them to improper fractions. Well, we know that 7 times 5 is 35, and 35 plus 3 is 38. So that first mixed number can be rewritten as an improper fraction, 38 over 5. We also know that 3 times 10 equals 30, and 30 plus 4 equals 34. So the second fraction can be rewritten as 34 over 10. And that means that the original problem that had two mixed numbers in it can be rewritten as 38 over 5 divided by 34 over 10. Now let me suggest at this point that you take the problem from here and see if you can finish out this division. Well, what do? You're going to have to switch it to multiplication first. We talked about this already. And you're going to switch that second fraction to its reciprocal. And when you do that, the division problem is rewritten as 38 over 5 times 10 over 34. You've now rewritten it as a multiplication problem, and now we just handle it as we have done in the past. Well, there are a couple of paths that you could take at this point. I might first suggest that we reduce the 10 over 34 as a fraction itself by a factor of 2 on both the top and the bottom, and turn that fraction alone into something that's more reduced. If you divide the 10 by 2 and you divide the 34 by 2, you'll see that that fraction is equivalent to the fraction 5 over 17. So we now know that the problem can be rewritten as 38 over 5 times 5 over 17. Now from there, I can cancel, right? I've got a multiplication problem in front of me. It's no longer a division problem, so I can start canceling some numerators and some denominators as I want. And in this case, those 5's can cancel pretty quickly, and I'm going to then be left with 38 over 1 times 1 over 17. And since 38 times 1 is 38, and 1 times 17 is 17, I know that my final answer is 38 over 17. Now, that's a perfectly fine final answer, but let me suggest that we rewrite it as a mixed number. We started the problem with mixed numbers. We might as well end with an answer that's also got mixed numbers in it. So, since 17 divides 38 a total of 2 times, and that has a remainder of 4, we know that 38 over 17 is the same as 2 and 4/17. Either of these is a perfectly fine way to write our final answer, but I wanted you to think about the improper fraction way as well as the mixed number way. Now, as we move forward, I'd like to work through a quick word problem that involves several of the issues I've already mentioned in this lesson, including some division with fractions. So here's the problem I want us to look at. Let's determine the exact number of yards that are in 19 1/2 feet. Now, as we approach this problem, let's remember a few facts. First of all, there are exactly 3 feet in a yard. Okay, so I'm going to need to know that as I go through this conversion. Secondly, in terms of estimation, let me ask you this question. If the problem had asked for the exact number of yards in 21 feet, what would you have said? Well, there are 7 yards in 21 feet because there's 1 yard for every 3 feet. But how did I get that 7? Well, if you think about it for just a moment, it's by computing 21 divided by 3. In other words, this is a division problem. That's exactly what this problem is asking, although the words in the original question didn't say division. Well, let's go back to that original problem now with this idea of division in mind. We weren't given 21 feet, we were given 19 1/2 feet. So what do we do to find the number of yards in 19 1/2 feet? Well, the exact same thing that we would have done for 21 feet. We want to divide the 19 1/2 by 3. So now my problem has been interpreted, if you will, or boiled down to computing 19 1/2 divided by 3. But we know how to handle this. If we just put together some of the ideas that we've seen earlier in this lesson, we can easily get 19 1/2 divided by 3. Well, let's walk through it together. First, 19 1/2 is a mixed number. Remember, if you see a mixed number in a division like this, you need to rewrite it as an improper fraction. Well, 19 times 2 is 38, and 38 plus that 1 is 39. So I can rewrite 19 1/2 as 39 over 2. My problem now is 39 over 2 divided by 3. What do I do next? I change that 3 to a 3 over 1 so that I make it look like a fraction as well. And I will have 39 over 2 divided by 3 over 1. Now what do I do? Notice we're doing these things step by step. Very important that we do those steps and we do them in the right order. What do we do next? We change that division to a multiplication and we rewrite the 3 over 1 as 1 over 3. And that means we now have 39 over 2 times 1 over 3. Now, what do? Now that it's written as a multiplication, we go through some cancellations, and you may not see it too quickly, but that 39 actually has a 3 in it as a factor. So I can cancel a 3 out of the 39, and I can cancel a 3 out of the 3, and that's going to convert my problem to 13 over 2 times 1 over 1. Where does the 13 come from? 39 divided by 3 is 13. And of course, 13 times 1 is 13, and 2 times 1 is 2. So my answer is 13 over 2, which is the same as 6 1/2 if you write it as a mixed number. So now let's interpret. We now know that 19 1/2 feet is the same as 6 1/2 yards. Now, before we move too quickly past this example, let's make sure that the answer really makes sense. First, we already noted that 21 feet is the same as 7 yards. Since we started with something that was fewer than 21 feet, I know that my answer needs to be smaller than 7 yards. And it was 6.5. That's a good sign. Next, it's also true that 18 feet is exactly 6 yards. Now, we started with more than 18 feet, so our answer should be more than 6 yards. And it is, it's 6.5. So again, this gives us confidence that our answer really is correct. Now, of course, there's one more way that we could check our answer. We could multiply our answer of 6.5 yards by 3 to convert it back to the number of feet, to see if we get back to 19.5. We did that kind of multiplication problem in the previous lesson. I'm going to leave it to you to calculate that if you'd really like to make sure we have the right answer. Now, over the course of the last few lessons, we've talked about adding, subtracting, multiplying, and dividing fractions. I hope that for some of you, I've been able to shed some light on the major steps you should take to complete these kinds of problems. Remember, it's often the case that you just need to go through the process one step at a time, in the right order of steps, and you'll be able to solve these problems with no trouble. Once you master each step and you remember what the order of the steps is, you'll be well on your way to mastering these essentials. Now, in our next lesson, we're going to turn a major corner. I want us to start talking about decimal numbers, how they come up in our everyday lives, how they're related to fractions, and how we add 2 decimal numbers and subtract 2 decimal numbers. I look forward to talking with you then.